Well, that was a close call. My camera cut out right as I was doing that, so filled up with storage. I gotta figure that out. I'm gonna go through my phone later and get rid of stuff. Anyhow, using centripetal force, right? So we just talked about centripetal force to determine the force of gravity. When you have the sun, right, and I'm gonna try to make a screencasting thing later to kind of talk about the simulation, and the Earth, right, the force of gravity is pulling it towards the sun, right? We're in the perfect stable orbit. And some of you might ask how that happened. Well, it turns out when the Earth condensed, so to speak, out of dust, right, gravitationally, dust particles attracted together and conglomerated, kind of like a snowball, really, to form the Earth. So it was all a big disk, right? You had like the young sun, and then you had this big disk of dust around it that was gravitationally attracted. And in that big ring of dust, right, the Earth condensed and swept through and became a planet. So it's in equilibrium. It's in I should say rotational equilibrium. It's got a constant angular momentum, which we don't really know about yet. But this force of gravity is literally, with force of gravitational attraction that we just calculated here, that is the force that is holding the Earth in its motion. It is the central acting centripetal force, which is why we talk about this force when we do circular motion. So that has to be times mv squared over r. It has to be equal to mv squared over r, the force of gravity, because force of gravity is keeping the mass of the Earth in its radius orbit at its velocity. So we can go and get it this way as well. So we already did this, right? We've got the mass of 5.97 times 10 to the 24th kilograms. Oh crud, what's the speed of the Earth in its orbit? Well, you can look it up online. It's 30,000 meters per second. You can look that up. But it's about 30,000, almost exactly. And then the radius, well, I shouldn't say exactly. It's really using these average numbers of the orbit is 1.49 times 10 to the 11th meters that we've already used. With the velocity of the Earth, you could kind of do that off as a side calculation. It's making one circumference lap in 1 year. So it's 2 pi times the radius of the Earth divided by 1 year. But the problem with that is we want it in meters per second to make this all work. So the top's easy, 2 pi times this radius. The bottom, 1 year, you got to convert to seconds times 365 days per year, 1 year, times 24 hours per day, times 3,600 seconds per hour, right? Cancels, 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 cancels. And that gets you down to seconds, which, I just plugged the whole thing into my calculator and got that 30,000. So we can go ahead and put in 30,000 there. 1,000 meters per second. Don't forget to square it. You know that's gonna trip you up. And when you plug this all in your calculator, you get a very nice number of 3.6 times 10 to the 22 newtons from doing the centripetal force. That and that agree? And it doesn't make sense for part C? Yeah, it has to be equal to each other because the gravitational attraction is literally the central acting force that keeps the Earth in orbit. It's kind of terrifying to imagine if gravity suddenly disappeared, we'd be going on our merry way around the sun. And this is, oh, by the way, these are not to scale at all. The Solar System Visualizer really does a good job showing you that. But we'd be going around the sun in our merry way, and then, well, gravity disappears, and we would just go flying off into the cold depths of space. Anyhow, that's it for the homework. kind of a big one. I apologize for that. I hope you didn't bust yourselves up too much on that. Well, we'll see you tomorrow on the interwebs.